Welcome to today's problem walkthrough. In this session, we'll be exploring problem number 277, titled Find the Celebrity. We'll dive into the problem requirements, analyze approaches, and discuss potential optimizations. Let's get started. Imagine you're at a party with N people, where each person is labeled from 0 to N1. Among these people, there's a potential celebrity. A celebrity is someone who is known by everyone at the party but doesn't know anyone else in return. Your goal is to figure out who this celebrity is, if one even exists. To help with this, you have access to a function called knows A, B. This function tells you whether person A knows person B. If person A knows person B, it returns true. Otherwise, it returns false. Using this, you need to identify the celebrity by returning their label, which is their index in the range 0 to N1. If no celebrity exists, you simply return -1. The output of the problem is straightforward. You return an integer that represents the label of the celebrity if one exists. If there's no celebrity at the party, you return -1. Let's look at an example to clarify. For n equals 3, we have 3 people at the party. The knows API tells us the relationships between these people. For instance, person 0 knows person 1, but person 1 does not know person 0. Similarly, person 0 knows person 2, but person 2 doesn't know person 0, and so on. Based on these relationships, the output is 2. This means person 2 is the celebrity. To explain this first example, we observe that person 2 does not know anyone at the party. This is evident because both knows 2, 0, and knows 2, 1 return false. Additionally, everyone at the party knows person 2, which we determine by the fact that knows 0, 2, and knows 1, 2 both return true. Since person 2 meets both conditions of being a celebrity, we conclude that they are the celebrity. In another example with the same input size of n equals 3, the relationships between people are slightly different. While person 0 and person 1 both know others, disqualifying them as celebrities, person 2 also fails to meet the criteria because not everyone knows them. Specifically, knows 1, 2 is false. Thus, no celebrity exists in this scenario, and the output is -1. Now, let's consider a smaller party with just 2 people. Here, person 0 knows person 1, while person 1 does not know person 0. Based on these relationships, person 1 satisfies both conditions of being a celebrity. They don't know anyone else, and they are known by person 0. Therefore, the output in this case is 1, meaning person 1 is the celebrity. This shows how even with a smaller group, we can use the knows API to determine the celebrity. To summarize, person 1 in the 2-person example is the celebrity because they don't know anyone, and they are known by the other person. This problem comes with some constraints that we need to consider. First, the number of people at the party can range from 2 to 10,000. The knows API can be called as many times as needed, but we want to minimize the number of calls to make our solution efficient. Some edge cases to keep in mind include situations where no celebrity exists, such as when everyone knows someone else. If there are only 2 people, the relationships must be verified directly. In cases where no one knows anyone, no celebrity exists, and we should return -1. Finally, when dealing with a large number of people, optimizing the solution to handle thousands of individuals efficiently is critical. Keeping these constraints and edge cases in mind will help us craft a robust approach to solve the problem. To tackle the problem of finding the celebrity, we first consider the brute force approach. The intuition here is straightforward. For someone to be a celebrity, they must be known by everyone else, but they themselves shouldn't know anyone. Using this logic, we check every person against all others to see if they meet these 2 criteria. Specifically, for each person I, we iterate over every other person J and check 2 things: does J know I, and does I know J? If someone satisfies both conditions for all others, we identify them as the celebrity. If no one meets the criteria, we return -1. This approach is simple to implement, but its major drawback lies in its inefficiency. Because of the nested loops, the time complexity is n squared. On the positive side, it uses constant space, but for large input sizes, it becomes impractical due to its high computational cost. A more efficient way to solve this problem is the optimized approach using two-pointer elimination. The key insight here is that we can systematically eliminate people who cannot be the celebrity based on the knows relationship. If person A knows person B, then A cannot be the celebrity. On the other hand, if A does not know B, then B cannot be the celebrity. Using this principle, we start with a candidate initialized to 0 and iterate through all the people. At each step, we use the knows API to determine whether the current candidate knows the next person. If they do, we eliminate the current candidate by updating it to the next person. Otherwise, we retain the current candidate. After this elimination phase, we are left with one potential candidate. To confirm their celebrity status, we perform a verification step, making sure everyone knows the candidate and that the candidate knows no one. This approach has a time complexity of O(n) for both the elimination and verification steps, making it significantly more efficient than the brute force method. Additionally, it uses only O(1) space, which is another advantage. Another approach to solving this problem is using a graph-based representation. Here, we model the knows relationship as a directed graph, where an edge from A to B indicates that A knows B. The celebrity, in this case, would correspond to a node with an in degree of n1, meaning everyone knows them, and an out degree of 0, meaning they know no one. To implement this, we use the knows API to build the graph as an adjacency matrix. Once the graph is constructed, we calculate the in degree and out degree for each node and identify the one that meets the celebrity criteria. While this approach provides a clear visualization of the problem, it has significant downsides. The time complexity is O(n) squared because of the graph construction, and it requires O(n) squared space for the adjacency matrix. These trade-offs make it less practical for large inputs, especially when compared to the optimized approach. Among the approaches considered, the optimized two-pointer elimination method stands out as the best choice. Both the brute force and graph-based approaches have O(n) squared time complexity, which makes them inefficient for larger inputs. In contrast, the two-pointer approach reduces the time complexity to O(n), while maintaining O(1) space complexity. This significant improvement in efficiency is achieved by eliminating non-celebrities in a single pass using the knows relationship. The final verification step ensures the solution is correct, with minimal additional work. While the two-pointer method is slightly more complex to implement than brute force, the efficiency gain far outweighs this drawback. The key realization here is that focusing only on plausible candidates drastically reduces redundant checks. This insight not only simplifies the problem but also provides a clear path to an optimal solution. Overall, the optimized approach offers the perfect balance between efficiency and simplicity, making it the ideal strategy for solving the find the celebrity problem. The task here is to identify the celebrity at a party with n people. A celebrity is defined as someone who is known by everyone else, but who personally knows no one. To solve this, we need an efficient algorithm. The brute force approach involves checking every person to see if they meet the two conditions. First, all others must know this person, and second, this person must not know anyone else. For each person I, we assume they are the celebrity and then verify these conditions by examining their relationships with every other person J. If both conditions are satisfied, I is the celebrity. Otherwise, we continue until everyone has been checked. If no one meets the criteria, we conclude there is no celebrity. While straightforward, this approach is computationally expensive because we must compare every person with every other person, resulting in a time complexity of O(n) squared. The brute force approach, while functional, is inefficient due to its quadratic time complexity. To address this, we can use an optimized strategy called the two-pointer elimination approach. The intuition here is that we do not need to check every relationship for every person, many can be eliminated early. We start by initializing two pointers, I and j, to represent two potential candidates. Using the knows function, we compare whether I knows j. If I knows j, I is eliminated as a candidate since a celebrity would not know anyone. On the other hand, if I does not know j, then j is eliminated because a celebrity must be known by everyone else. We repeat this process until only one candidate remains. This person is our potential celebrity. But since elimination alone does not guarantee that the candidate satisfies both conditions, we must validate the remaining candidate. Once we have identified a potential celebrity using the elimination process, the next step is validation. For the remaining candidate, C, we verify that all others know C and that C knows no one else. If either condition fails, we return -1, indicating that no celebrity exists. This validation step ensures the correctness of the solution. The overall time complexity of the optimized approach is O(n). Candidate identification requires a single pass over the n people, and validation involves another pass, making the process linear. The space complexity remains O(1), as we use only a few pointers and no additional data structures. Key insights here include the efficiency of the elimination principle, which allows us to identify a single candidate in n1 comparisons, and the importance of the validation step to confirm the result. The nose function is central to the algorithm, abstracting the relationship checks and enabling modularity. To ensure the algorithm handles all scenarios, we must consider edge cases. For example, if there is no celebrity, the algorithm should correctly return -1. Similarly, if there are conflicting relationships where multiple people seem to qualify, the validation step ensures that no false positives occur. If everyone knows everyone, or no one knows anyone, the algorithm must handle these cases without errors. The pseudocode for the optimized approach begins with identifying the candidate. Starting with the first person as the initial candidate, we iterate through the group, using the nose function to eliminate non-candidates. Once a candidate is found, we validate them by checking their relationships with all other individuals. If the candidate fails validation, we return -1. Otherwise, we return the candidate as the celebrity. This structured approach ensures clarity and correctness in implementation. The complexity analysis of the optimized algorithm shows its efficiency. The candidate identification step requires O(n) time, as each comparison eliminates one candidate, and we only make n1 comparisons. The validation step also takes O(n), as we check the relationships of the remaining candidate with the rest of the group. Combining these steps, the total time complexity is O(n). The space complexity is O(1), because no additional data structures are required, only a few pointers are used. This makes the algorithm highly efficient in scenarios with large groups. By leveraging the elimination principle and minimizing redundant checks, this approach provides a significant improvement over the brute force method, making it both faster and more elegant. This solution efficiently solves the find the celebrity problem using a two-step approach. The goal is to find one person, if any, in a group of n individuals who is known by everyone but knows no one. Step-by-step explanation. 1. The knows API. This function is predefined and allows us to check whether person A knows person B. This is the core utility for solving the problem. 2. Initial setup. We define a variable candidate, initialized to 0, which we will update as we iterate through the group to identify a potential celebrity. 3. Step 1. Candidate selection. We iterate through the group, from 1 to n1. If the candidate knows another person I, then candidate cannot be the celebrity because a celebrity knows no one. We update candidate to I. By the end of this loop, candidate points to a person who might be the celebrity. 4. Step 2. Candidate verification. We verify if the chosen candidate satisfies the celebrity conditions. They must not know anyone else. Everyone else must know them. For each person I, other than the candidate, we check. If candidate knows I, they cannot be the celebrity. If I does not know candidate, they cannot be the celebrity. If any of these conditions fail, we return -1, indicating no celebrity exists. 5. Return the candidate. If the candidate passes verification, we return their index as the celebrity. Complexity. Time complexity. The algorithm runs in O(n) time because Step 1 makes one pass through the group, O(n). Step 2 makes another pass for verification, O(n). Space complexity. The solution uses O(1) additional space since no extra data structures are used. This solution is optimal and ensures correctness by systematically narrowing down potential candidates and validating the final choice. Here, we are implementing the solution to find the celebrity in a group of n people. The class begins with the knows method, which is provided by the LeetCode framework. This function checks if person A knows person B. The implementation of this method is hidden, as it's handled internally by the problem framework, so we don't need to modify it. Now, in the Find Celebrity method, the first step is to identify a potential celebrity. We initialize the candidate as the first person, 0, and iterate through the rest of the people using a for loop. If the current candidate knows the next person, it means the candidate cannot be a celebrity, so we update the candidate to the current person. By the end of this loop, we have a single candidate who might be the celebrity. The second step is to verify this candidate. We loop through all people again, checking two conditions: if the candidate knows anyone, or if there's anyone who doesn't know the candidate. If either condition fails, we return -1, indicating there is no celebrity. Finally, if the candidate passes all verification checks, we return the candidate as the celebrity. This completes the implementation. The logic ensures that the solution is efficient, as we only make one pass to identify the candidate and another pass to verify the candidate, resulting in an overall time complexity of O(n). This approach leverages the properties of the celebrity problem, specifically, the fact that a celebrity is known by everyone but knows no one. The implementation is concise and adheres to the constraints of the problem. In LeetCode problem number 277, Find the Celebrity, the task is to determine if there is a celebrity among a group of n people at a party. A celebrity is defined by two conditions: first, they are known by everyone at the party, and second, they do not know anyone else. To solve this, we are given an API function knows A, B, which returns true if person A knows person B. The solution involves two main steps. First, we identify a potential celebrity by iterating through the group and narrowing down to one candidate. Then, in the second step, we verify whether that candidate satisfies both conditions of a celebrity. This approach ensures that we efficiently solve the problem in a structured way. Now, let's look at an example where a celebrity exists. Suppose there are 4 people at the party, and their relationships are as follows: person 0 knows persons 1, 2, and 3, person 1 knows persons 2 and 3, person 2 knows nobody, and everyone knows person 2. To identify the celebrity, we start with candidate 0. Comparing candidate 0 with others, we find that knows 0, 1 is true, meaning candidate 0 knows person 1, so we update the candidate to 1. Next, knows 1, 2 is true, so we update the candidate to 2. Finally, knows 2, 3 is false, so candidate 2 remains unchanged. By the end of this step, we have identified person 2 as the potential celebrity. The next step is to verify whether this candidate, person 2, is indeed the celebrity. To do this, we ensure that person 2 knows no one, and that everyone knows person 2. First, checking if person 2 knows anyone, we find that knows 2, 0, knows 2, 1, and knows 2, 3 are all false, satisfying the condition that the celebrity knows no one. Then, we check if everyone knows person 2. The results of knows 0, 2, knows 1, 2, and knows 3, 2 are all true, satisfying the condition that everyone knows the celebrity. Since both conditions are met, the final output is person 2 is the celebrity. In another example, we examine a case where no celebrity exists. Here, there are 3 people, and the relationships are as follows: person 0 knows person 1 knows person 2, and person 2 knows person 0. Starting with candidate 0, we compare with others. Since knows 0, 1 is true, the candidate is updated to 1. Then, knows 1, 2 is true, so the candidate is updated to 2. By the end of this step, we identify person 2 as the potential celebrity. We then verify if person 2 satisfies the conditions of being a celebrity. First, checking if person 2 knows anyone, we find that knows 2, 0 is true, which violates the condition that a celebrity knows no one. Since the candidate fails this verification step, we conclude that there is no celebrity in this group. The final output is -1, indicating that no celebrity exists in this scenario. Additionally, this example highlights how the algorithm handles cases where the relationships form a cycle. Finally, consider the edge case where there is only a single person, n equals 1. In this scenario, the algorithm begins by identifying the sole individual, person 0, as the candidate. Since there are no other people at the party, no comparisons are required. During the verification step, the conditions for a celebrity are trivially satisfied, as there is no one for person 0 to know or be known by. Therefore, the final output in this case is 0, confirming that the single person is the celebrity. The time complexity of our algorithm is broken into two main steps. First, we identify a potential celebrity by iterating through all n people. During this process, for every person I from 1 to n1, we call the knows candidate I function to check if the current candidate knows the next person. This results in exactly n1 calls to the knows function, making the time complexity for this step O(n). Next, we verify the candidate by ensuring they meet the two celebrity conditions. The candidate must not know anyone else, and everyone else must know the candidate. For each person, excluding the candidate, we make two calls to the knows function, one to check if the candidate knows them and one to check if they know the candidate. This results in 2 n1 calls to knows, or O(n), time complexity for this step. Adding both steps together, the total number of knows calls is n1 plus 2 n1 equals 3 and 3, which is linear in n. Therefore, the overall time complexity of the algorithm is O(n). The space complexity of the algorithm is straightforward. It uses a constant amount of extra space, as we only require a few integer variables like candidate and I. These variables do not scale with the input size n. Additionally, we do not use any extra data structures, and the knows API operates in O(1) space. Thus, the overall space complexity of the solution is O(1). When analyzing the best, average, and worst cases, we find that the algorithm always performs exactly 3 and 3 calls to the knows API, regardless of the input or the position of the celebrity. This consistency means that the time complexity remains O(n) across all cases, without variation. To better understand the efficiency of this approach, let's compare it to the brute force method. In the brute force approach, for each person I, we check if they meet the celebrity conditions by iterating over all other n1 people. For each of these checks, we make 2 n1 calls to the knows function, leading to a total time complexity of O(n squared). However, the optimized approach drastically reduces this by first identifying a single candidate in O(n) time and then verifying the candidate in another O(n) step. This reduces the total number of knows calls to 3 and 3, making the time complexity O(n). Importantly, both approaches maintain a space complexity of O(1), as no additional space is used. The key advantage of the optimized approach lies in its linear time complexity compared to the quadratic complexity of brute force. To solidify our understanding, let's break down the mathematical proof of the algorithm's big O complexity. In step 1, we loop n1 times, making one knows call per iteration. This step has a time complexity of O(n). In step 2, we loop through all n people, making exactly 2 knows calls per person. This step is also O(n). When we combine these two steps, the overall time complexity becomes O(n) plus O(n), which simplifies to O(n). The space complexity remains O(1) throughout, as no additional data structures are used and variable usage is constant. In summary, this optimized approach achieves a time complexity of O(n) and a space complexity of O(1). It is significantly more efficient than the brute force method, reducing the time complexity from O(n squared to O(n), while maintaining constant space usage. One of the most common mistakes is misunderstanding the problem statement itself. Remember, the celebrity is defined as someone who does not know anyone else, meaning their entire row in the knows matrix, except for the diagonal representing themselves, should contain only zeros. If this condition is not met, you've violated the fundamental definition of a celebrity. Additionally, simply assuming that the last candidate derived from the elimination process is automatically a celebrity is another frequent error. While the elimination narrows down the possibilities, you still need to validate that the candidate satisfies both conditions: they know no one, and everyone else knows them. Finally, using a brute force approach to check every pair of people results in an O(n squared) time complexity, which is inefficient. This problem can be solved much faster, in O(n), using optimized strategies like a stack or pointer-based approach. Another common pitfall is incorrect matrix indexing. For instance, if you confuse knows A, B with knows B, A, you'll misinterpret the relationship between people, as the directionality matters. If knows A, B is true, it means person A knows B, not the other way around. Failing to account for this can result in completely incorrect results. Additionally, it's critical to handle edge cases explicitly. For example, if no celebrity exists because everyone knows someone, or when the matrix represents just one person, n equals 1, neglecting these scenarios can lead to runtime errors or invalid outputs. Carefully addressing these edge cases ensures your solution is robust and reliable. This problem is often a variation of finding a universal sink in a graph. Recognizing this pattern can help you adapt similar algorithms to solve it effectively. The most optimal approach is the elimination strategy, which operates in O(n) time complexity. This is typically the expected method in interviews, so it's important to master it. Interviewers may also challenge your understanding by asking about edge cases, such as when no celebrity exists, when all entries in the nose matrix are false, or when there's only one person in the matrix. Being able to explain these scenarios demonstrates depth in your understanding. Lastly, be prepared to discuss trade-offs. For instance, while the brute force approach is simple and straightforward, it's inefficient compared to the optimized O(n) solution. Highlighting these trade-offs shows your ability to balance simplicity and efficiency. To deepen your understanding, it's helpful to explore related problems. The direct problem we're addressing here, LeetCode 277, Find the Celebrity, is a great starting point to master the elimination strategy. Another similar problem is LeetCode 997, Find the Town Judge, which also involves directed relationships but with slightly different criteria for identifying the judge. Beyond these, LeetCode 261 Graph Valid Tree focuses on graph connectivity and acyclic properties, which are useful concepts when working with graph-based problems. Lastly, LeetCode 841 Keys and Rooms emphasizes graph traversal and connectivity, reinforcing skills that are indirectly applicable to solving problems like this. Working through these problems can help you build a strong foundation in handling relationship-based challenges. When considering alternative approaches, the brute force method involves comparing every pair of people, resulting in an O(n)² time complexity and O(1) space complexity. It's simple to implement but inefficient for larger inputs. A stack-based elimination strategy improves the time complexity to O(n), but it requires O(n) additional space for the stack. This approach is faster but uses more memory. The two-pointer approach, however, is both time and space efficient, with O(n) time complexity and O(1) space complexity. While optimal, it can be trickier to implement correctly on the first attempt. Each approach has its trade-offs, but in interviews, the stack-based or two-pointer method is often preferred due to their efficiency and alignment with the problem's constraints. Great job reaching the end of this problem walkthrough. To summarize, we tackled the Find the Celebrity problem, discussed efficient approaches, and highlighted key takeaways. Don't forget to like, subscribe, and stay tuned for more coding challenges. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!